This is about first law of thermodynamics, and we were gonna talk about the isobaric process. A thermodynamic process that occurs at constant pressure is called an isobaric process. The Greek terms iso and baros, which both signify equal pressure, are where the name isobaric originates. As a result, when the volume is increased or decreased, the pressure is remaining constant. In essence, this cancelled out brought on by heat transmissions. Before we get the equations, let us talk about the fundamental of the first law of thermodynamics. It states that energy cannot be generated or destroyed in a system of constant mass, but it can be changed from one form to another form, accordingly to the first law of thermodynamics, and it is originated also from the principle of law of energy. Now, let us consider a situation. There is a quantity of gas that is kept in a constant temperature in a cylinder with a frictionless piston and has a heat of amount Q is being delivered into the system. The gas produces the required amount of work by expanding and absorbing this heat. Mathematically, we can express the first law of dynamics into this formula, that is Q equal to W plus delta U, where Q is the quantity of the heat supply onto the system. W is the work done onto the system or being delivered out from the system. And delta U is a change in internal energy of the enclosed system. Since thermodynamics talks about the net heat transfer to or out of the system, so the sign convention is important in the calculation, especially for the isobaric process where heat is being added to the gas as it being heated and increasing delta U and work done by the gas in which pressure of an enclosed system is constant. For instance, when heat flows into the system, the value Q should be in positive, whereas value of Q is in negative when heat is transferred out of the system. The formula for the isobaric process is W equals to integrate PV delta V, whereas we can expand to integrate PV2 minus PV1.
Now I will tell about the example in daily life. Mechanical energy converters that turns mechanical energy into heat include refrigerator and heat pumps. These are typically categorized as closed systems. The temperature of a gas increases when it is compressed. The environment can then get heat from this hot gas. Since some of the compressed gas heat energy was losing during the hot cycle, when it is allowed to expand, its temperature falls below what it was before compression. The cold gas can then absorb heat energy from its environment, and air conditioner functions on the same principles. Instead of producing cold, air conditioners take away heat. The working fluid is moved outside where it is compressed and heated by a mechanical pump. The heat is then frequently transported to the environment outside using a heat exchanger that is air-cooled. It is then transported indoors where it can expand and cool before absorbing heat from the interior air via a different heat exchanger. In essence, a heat pump is a reverse cycle air conditioner. The building is heated using the heat from the compressed working fluid. Then it is taken outside, it cools and expands, enabling it to absorb heat from the ambient air, which is typically warmer than the chilly working fluid.
The question here states that why is the first law of thermodynamics important to the environment? The answer to the previous question, as we all may already know, is that the sun is the only source of energy for every living thing on Earth. Herbivores that consume green vegetation acquires these energies from plants instead of returning them to the solar system. Some of the energy that herbivores had gained is utilized by predators or transferred to decomposers when they die. Another question that we have here is, air is contained in a vertical piston cylinder assembly fitted with an electrical resistor. The atmosphere exerts a pressure of 101.33 kilopascal on the top of the piston, which has a mass of 4.5 times 104 gram and a face area of 0.09290 meters square. Electric current passes through the resistor and the volume of the air slowly increases by 45.31 liter while its pressure remains constant. The mass of the air is 0.27 kg and the temperature of air increases from 25 degrees Celsius to 84.3 degrees Celsius. The air and piston are at rest initially and finally. The piston cylinder material is a ceramic composite and thus a good insulator. Friction between the piston and cylinder wall can be ignored. The local acceleration of gravity is G equal to 980.66 cm over second square and the specific heat capacity of air is C air equal to 1.012 joule per gram per Kelvin. Determine the internal energy of the air in kilojoule for a system consisting of the air alone.
There are a few assumptions that we can use in these questions, which are: first, two closed systems are under consideration as shown in the schematic. 2. The only significant heat transfer is from the resistor to the air, during which the air expands slowly and its pressure remains constant. 3. There is no net change in kinetic energy. The change in potential energy of the air is negligible, and since the piston material is a good insulator, the internal energy of the piston is not affected by the heat transfer. 4. Friction between the piston and cylinder wall is negligible. And lastly, number 5 is the acceleration of gravity is constant. G equals to 9.866 meter per second square.
Hi, my name is Lin Kok Yo. So right now I'm going to present you guys the solution of these thermodynamic questions. So from the question, we can notice that this is the vertical piston cylinder, and the question, we also can receive some information from the question as well, such as atmospheric pressure we get is 101.3 kilopascal. The mass of piston is 4.5 multiplied 10 to the power of 4 gram. The area of piston is 0.09290 meter square. The mass of the air is 0.27 kilogram. And for the change in volume of the air is 45.31 liter. And we also can notice that the initial temperature is 25 degrees Celsius, and the final temperature of the air is 33.4 degrees Celsius. So let's move on to the solutions. So for step 1, taking the air as the system, the energy balance reduced with assumption 3 to solving for change in internal energy of the air, which are the theta U and air. So we notice that through the energy balance, we can cancel out the kinetic, the change in kinetic of energy, and the change in potential of energy, So it will let us with the equation of change of internal energy of the air equals to the heat transfer minus the work done. So for step 2, from this system, work is done by the force of pressure, which are P, acting on the bottom of the piston as the air expands. So with assumption of constant pressure, we can state that work is equal to integrate from V1 to V2. P is the pressure, then included dV. So then it will be equals to pressure bracket B2. B2 is the final volume of the air minus B1. B1 is the initial volume of the air. Okay. Alright. So by applying the function method, we are able to find the work done, which are W. So let us change W into Fx. So we can say that Fx are equals to P bracket B2 minus V1. So for step 3, we are going to determine the pressure P. We use a force balance on the slowly moving frictionless piston, and the upward force extended by the air on the bottom of the piston equals the weight of the piston plus the downward force of the atmospheric acting on the top of the piston. So in symbol are there. So P, we know this is the pressure. So A piston is actually the area of the piston, equals to mass of the piston multiplied with the gravitational acceleration, which are G, and plus the atmospheric pressure, and we can multiply with the area of the piston. So our step 4 actually is just like substitute the value inside this equation. Okay, so in order to find P, so I do a little bit of rearrangement, which are the pressures are equals to mass of the piston multiplied with the gravitational acceleration over the area of the piston and plus the atmospheric pressure. Okay, so we know that the mass of the piston is equals to 4.5 multiplied 10 to the power 4 gram, and the gravitational acceleration is 9.8066 meter per second square, meter per second square. So we can, and the area of piston is 0.0929 meter cube. So in order for us to find the answer in Newton per meter square, we need to multiply with 1 Newton. We need to multiply 1 Newton over 1 kg meter per second square, and we need to multiply with 1 kg in order to change the value in kg. So we need to multiply 1 kg and divide by 1000 gram. Then for the atmospheric pressure, we need to change it. We need to change to Newton per meter square. So we need to so the atmospheric pressure, which are 101.33 kilopascal, we need to divide by 1000, which are 10 to the power 3 kilopascal, and we multiply with 1 Newton per meter square. Then at last we will get the answer as 4.75 multiplied 10 to the power 3 Newton per meter square. Okay. Then thus we are able to find the Fx answer. So we are able to find the Fx answer. So since we already found the pressure, so right now we just substitute the pressure inside the formula, and we notice that the change in volume of the air is actually 45.31 liter. So we just multiply together, and we wanted, because the question asks us to change the value in kilojoule. So in order to change it to kilojoule, we do multiply 0.02817 meter cube over 28.317 liter in order to get meter cube. And in order to get kilojoule, because we noticed even we multiply, we will get like Newton multiplied with meter. So in order to cancel out, we need to multiply 1 kilojoule and divided by 10 to power 3 Newton multiplied with Newton meter. Okay. So at last we will get our answer as 0.2152 kilojoule. So we notice that Fx equals to W, which are work done. So our final answer for work done is 0.2152 kilojoule. So continue on step 5. So to determine the heat transfer from the resistance to the air, which are Q. So we're still following the assumption tree. We found Q, which there is no heat loss to the surrounding. Heat transfer formula can be expressed as Q equals to the mass of the air. C air is actually the specific heat capacity of the air, and multiply with the change in temperature. So by using the application of function, we are able to find Q. So we just let H bracket X equals to Q. Then we just change it to Hx equals to M. Just right now we just change Hx equals to M is mass of air multiplied with the specific heat capacity of air and the change in temperature. So right now we just substitute all the value we get from the questions into the formula, and right now we will get like 0.27 kg multiplied by 1.012 joule per gram per Kelvin, and we need to change the temperature from degree Celsius to Kelvin. So we need to plus. So the final like for change in temperature, right? We change. It's actually the final temperature. Final temperature minus the initial temperature. So our final temperature is actually 84.3. So we need to change it to Kelvin value. We just need to plus 273.15. Same goes as our initial temperature. And it's not finished yet because we want to change our answer into kilojoule. So as you can see, the mass of the air is 0.27 kilogram. So we need to change it to gram. So we need to multiply with 1000 gram, then divide by 1 kilogram. And in order to change from joule to kilojoule, we need to multiply 1 kilojoule and divided by 10 to power 3 joule. Then at last, we'll get our answer as 16.20 kilojoule. So hence, for our heat transfer will be equals to 16.2 kilojoule. So, and this is our last step, which step 6, is to determine the change of internal energy of the air, theta U in air. Okay, so we just use back the first step of the formula, which the change in internal energy of the air equals to Q is the heat transfer minus the work done. So we just take a value. The Q is, for the heat transfer, the value is 16.2 kilojoule minus the work done, which are 0.2152 kilojoule. Then at last, we'll get our answer as 15.98 kilojoule. So that's all for the solution. Thank you.